Hello, everybody, and welcome to the second video for week 10. So just a reminder, because there's no in-person session on Thursday, this video might be a little bit longer than usual. And also there's no quiz on Thursday. Okay, so today we're going to talk about quadratic reciprocity. So this last law, and also sort of the rule for when 2 is a square mod p. So this last two properties of the Legendre symbol when we made this list. And we're going to talk about how you justify those, how you explain why those hold. So going beyond just sort of seeing that they hold in examples and claiming that they hold, but really understanding why they hold. And we won't give a complete justification, but we'll see what the key ideas are. So to begin with, I just want to go over a extended example. Okay, so this is going to be about what happens in quadratic reciprocity when you take one of the primes to be 3. And we're going to set it up as follows. So if I go back and I look at the properties of the Legendre symbol, if I assume that they hold, then I can write that the Legendre symbol of -3 over p is equal to the Legendre symbol of p over 3. That's 1 if p is congruent to 1 mod 3 and 2 if p is congruent to 2 mod 3. So somehow this combines two of the things. This combines quadratic reciprocity for 3 over p plus the rule for when -1 is a square mod p. But somehow if you combine those two, then you get a simpler formula than you get just for quadratic reciprocity for 3 mod p. Okay, so this we know is true if we sort of assume all these properties of the Legendre symbol. And what I want to do in this example is sort of directly give an explanation of why the Legendre symbol of -3 over p is 1 if p is congruent to 1 mod 3 and 2 if p is congruent to 2 mod 3. Okay, so we're going to justify this directly. So let's start in the case when p is congruent to 1 mod 3. So if we're saying that Legendre symbol of -3 over p is 1 if p is congruent to 1 mod 3, what that means is we need to show that -3 is a square mod p. And sort of conversely, for the second one, we'll need to show that if p is congruent to 2 mod 3, then -3 is not a square mod p. So conceptually, it's a little bit easier to start with this first case. And yeah, okay, so start with the first case. So somehow it's easier to show something is a square than to show it's not a square, at least for me, because somehow to show something is a square, one way to do is you can just give a formula for a square root. Whereas to show something's not a square, you sort of have to show that there's no possible formula for a square root in some sense. So that's what we're going to do in this first one. We're going to sort of show that when p is congruent to 1 mod 3, that there is a square root, and so we can do it by sort of explicitly constructing a square root. And so this is building off of these formulas we did in class, where we expressed square roots in terms of roots of unity. Okay, so how are we going to do this? Well, if p is congruent to 1 mod 3, then by part 5 of exercise 2 on this week's homework, I can choose a primitive third root of unity zeta in fp. So somehow the condition for there to be a primitive third root of unity in fp is exactly that p be congruent to 1 mod 3. And you're supposed to justify this on that exercise, but let me just sort of recall the reason. So the reason is, well, let me just state the reason. I guess I'm not really recalling it if you haven't done the homework yet. So this might help with the homework. The reason is sort of saying zeta cubed is equal to 1. So saying that you're a third root of unity and that zeta is not equal to 1. Well, if I apply discrete log, I just pick some base for discrete logarithm. That means so 3 times I of zeta is equal to I of 1, which is 0, and I of zeta is not equal to 0. So then you just have to understand, well, I of zeta, this inverse logarithm takes values in z mod p minus 1z. So you have to understand, when is there a non-zero solution? to 3y is equal to 0 in z mod p minus 1z. So here y is I of zeta. So you're sort of solving for what I of zeta can be. And well, it's, if you think about that, I mean, you're just sort of asking when can you sort of find an integer such that 3 times that integer is divisible by p minus 1. In order for that, so when you can find when can you find an integer that's not divisible by p minus 1, such that 3 times that integer is divisible by p minus 1? Well, the only way that's possible is if 3 itself divides p minus 1. Okay, so you'll think about that when you think about this exercise, but that's the reason the statement holds, that p is congruent to 1 mod 3 if and only if there's a primitive third root of unity in FP. Okay, but good. So once I have that, I can just pick one of those primitive third roots of unity. So some solution to this equation. And then once I have this, then I claim that zeta, zeta is my primitive third root. And if I look at zeta minus zeta squared, well, that's some element of FP. And I claim that that's actually a square root of minus 3 in FP. So that zeta minus zeta squared, take that whole quantity, I square it, I get minus 3. So on the worksheet and like in class on Tuesday, what we saw is like if you took zeta to be a primitive third root of unity in the complex numbers, so if you took like zeta to be e to the 2 pi I over 3, then this identity holds in the complex numbers. You also sort of see that if you just sort of pick some values of p, like we did like p equals 7, I think, and you sort of stick, you compute some. Sorry, I had to let my dog out of the computer room. So if you let p be equal to 7 and you just compute a primitive third root, in that case, you could take it to be like zeta to be 2. Then you can just plug it in here and see that what you get is minus 3 in FP. So we sort of saw this in some examples, but actually more generally, this equality holds sort of in any field whenever you have a primitive third root of unity in that field. So let me sort of explain why that is. So if we look at zeta minus zeta squared, and you just expand that out, well, you get zeta squared. Then the cross terms give you minus 2 zeta cubed plus zeta to the 4th. But sort of somehow by definition, zeta cubed is equal to 1. So I can get this first term, I'll just leave as zeta squared, but this zeta cubed is just 1. And by definition, because zeta is a third root of unity, like zeta cubed is 1. And then I sort of factor out a zeta cubed out of zeta to the 4th, I just get zeta. So I get zeta squared minus 2 plus zeta. And then I just reorganize, I'm going to write that as zeta squared plus zeta minus 2. Okay, so if I want to show this thing is equal to minus 3, I just have to show that zeta squared plus zeta is equal to minus 1. Okay, so that's what I have left to do. So up here, and so far I only used that zeta was a third root of unity. I didn't use that it was a primitive third root of unity. I mean, sort of everything I said so far sort of applies if I let zeta be equal to 1. But of course, if zeta is equal to 1, this is just 0. So this does not sort of square to minus 3. So I didn't somehow, at some point, I'm going to have to use something specific to zeta being a primitive third root of unity. And that's what I'm going to do that now. So since zeta is a third root of unity, it's a root of x cubed minus 1. But on the other hand, it's not, since it's primitive, it's not a root of x minus 1. So it's not equal to 1. So if it's a root of x cubed minus 1, but not a root of x minus 1, it's a root of the quotient, which is the polynomial x squared plus x plus 1. So you can just check that by long division if you want, or you can just remember this from when you're doing geometric series in calculus. Okay, but in saying your zeta is a root of x squared plus x plus 1, that just means zeta squared plus zeta plus 1 is equal to 0. So that's what I get when I plug in zeta here. And if I rearrange that, that means zeta squared plus zeta is equal to minus 1. So I just brought this 1 over here. So zeta squared plus zeta is equal to minus 1. And that's exactly what I wanted to see. Okay, and so just to recap, this thing, so I took zeta squared minus zeta and I squared it. I expanded out and simplified. I got zeta squared plus zeta minus 2. And then I'm using this right here to substitute zeta squared plus zeta is minus 1. And so I got minus 3. So indeed, sort of zeta squared minus zeta is a square root of minus 3. And because zeta was an FP, sort of zeta squared minus zeta, this is just an element of the FP. And so that means sort of minus 3 is a square mod P. Okay, so going back up, what I verified is that I verified that if P is congruent to 1 mod 3, then minus 3 is a square mod P. And I did it by sort of using P congruent to 1 mod 3 to get a primitive third root of unity, and then expressing the square root of minus 3 using that primitive third root of unity. So I sort of write down a specific formula for it. Okay, so what if P is congruent to 2 mod 3? So in that case, there's no primitive third root in FP. I mean, the same exercise or the same justification I gave above when P is congruent to 1 mod 3 sort of also will show you that when P is congruent to 2 mod 3, there's no primitive third root of unity. And so in some sense, that means the formula doesn't work. I mean, it means I can't this thing I did up there is not going to work to produce a square root of minus 3. I can't just choose a primitive third root of unity, write down this formula and get a square root of minus 3. But somehow, I mean, just because one formula doesn't work doesn't mean there's no way to sort of get a square root of minus 3. It just means, that specific way of getting a square root of minus 3 doesn't work. And somehow I haven't really answered because some of there still could be a square root of minus 3 that you just got some different way. But in fact, there's not. And this is sort of something really special about this specific case we're looking at, where we took sort of our prime to be 3, because we can actually reverse the formula. So above we use that sort of if we had a primitive third root of unity, we can get a square root of minus 3. But in fact, if we start with a square root of minus 3, we can also get a primitive third root of unity. So to see that, let me just recall that in the complex numbers, well, you can take a primitive e to the 2 pi I over 3 is a primitive third root of unity. And then using Euler's identity, I can write that as the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. If you sort of dig up some trigonometric tables, you'll see that that's minus 1 plus I times square root of 3 all over 2. Okay, but now somehow I can solve, not solve, so this gives me a formula. I times square root of 3, that's a square root of minus 3. And so this gives me a formula for e to the 2 pi I over 3 in terms of a square root of minus 3. And in fact, sort of this formula holds in any field where we can divide by 2. So any field where 2 is invertible. So for example, it doesn't hold in F2, but it does hold in F3 and F4, or F3 or F5 and F7 sort of, as long as you have a square root of minus 3. So if you have a field and you have a square root of minus 3, so some alpha such that alpha squared is minus 3, then you can check that minus 1 plus alpha over 2 really gives you a primitive third root of unity. And you do the same sort of thing. You just expand out minus 1 plus alpha over 2 cubed, and you sort of use the fact that alpha squared is equal to minus 3 to simplify what you get, and you expand that out. Okay, so I'll sort of leave that as an exercise. But so the point is sort of, if you have a square root of minus 3, you really also have a primitive third root of unity. And so because of that, sort of this first one, okay, so this statement is actually an if and only if. So if P is congruent to 1 mod 3, if and only if minus 3 is a square mod P. Because we have P is congruent to 1 mod 3, if and only if there's a primitive third root of unity mod P. And now we've said that that's if and only if there's a square root of minus 3 mod P. Okay, but sort of if this is an if and only if, then sort of this also has to be an if and only if, just because sort of if P is not congruent to 1 mod 3, then it has to be congruent to 2 mod 3. And sort of if minus 3 is not a square mod P, then sort of minus 3 is not a square mod P. So somehow this is the other option. Okay, so good. So that sort of gives a full and complete justification of this statement that we sort of know that sort of somehow this encodes quadratic reciprocity for the prime 3. So just to sort of summarize that, right, this example, when combined with sort of this multiplicativity, which we've sort of already established using the formula from last time for the Legendre symbol. So when combined with this multiplicativity and the formula for -1 over p, which again we've already sort of established last time, sort of if you sort things out, you see that what you really get by combining that example with these two identities is the quadratic reciprocity law for p equals 3, which looks like sort of the Legendre symbol of 3 over q is -1 to the q minus 1 over 2 times the Legendre symbol for q over 3. I probably am missing a minus sign. Oh no, I think this is good, sorry. Yeah, good. Okay, so that's what it looks like for quadratic reciprocity when p is equal to 3. And basically what we want to do to sort of understand quadratic reciprocity in general is do something similar. Sort of use roots of unity and sort of express square root of p as a formula using sort of p fruits, or using roots of unity, using p fruits of unity. But this gets a little bit harder for p greater than 3. So for 2 reasons. So one reason is it's just a little bit harder to understand like how you can write down a formula for a square root of p or square root of minus p using primitive roots of unity. Sorry, this should say in terms of a primitive p fruit of unity. So we want to write down a square root of p or minus p in terms of a primitive p fruit of unity. This is sort of harder to do, but it can be done. But then actually, even once you've done it, this argument, even once you've done this argument for establishing quadratic reciprocity, it gets a little bit more complicated because it's no longer the case that sort of you can reverse the formula. So it will still always be true that we can write a square root of p or minus p in terms of a primitive p fruit of unity, but it will no longer be true that we can go back in the other direction and write the primitive p fruit of unity just using the square root of p or minus p. Okay, but let's at least state what the formula is for square roots in terms of primitive p fruit of unity. It's a little bit complicated, but in the end, it's not too bad to verify, although we're not going to do it. But this is sort of due to Gauss. And it says if zeta is a primitive p root of unity in any field, and p, where p is an odd prime, then if I take the sum from I equals 1 to p minus 1, so this is all of the non-zero elements in FP, and I take the Legendre symbol of I over p times zeta to the I, then this thing gives me a square root of, well, either p or minus p. So it gives me a square root of -1 to the p minus 1 over 2 times p, which is just a square root of p. That means it's a square root of p if p is congruent to 1 mod 4, or minus p if p is congruent to 3 mod 4. Okay, so this formula for zeta 3 was, or so this formula for a square root of -3 was a special example of this. I mean, there we just had I is 1 and I is 2. And so the first coefficient was 1 and the second coefficient was -1. And here we're in the 3 mod 4 case, so we got sort of -3. So that's a formula for the square root of -3 was a special case of this more general result. And sort of the other formula we wrote down on the worksheet that you guys have looked at, hopefully, or will look at soon, is that is the case when p is 5, so zeta is a primitive fifth root of unity, then zeta plus zeta fourth minus zeta squared minus zeta cubed gives you a square root of 5. So now there's no minus sign because sort of 5 is congruent to 1 mod 4. So again, this is sort of something on the homework. You're going to verify over the complex numbers just by expanding it out and using sort of basic trig formulas. And then you're also going to verify in a special case, sort of just for a specific finite field and a specific primitive fifth root of unity. But really, this is a completely general fact. This is sort of, I mean, I mentioned this in class, but let me mention it again. It's sort of amazing that you can sort of write down identities that hold sort of both over the complex numbers and over finite fields, even though so somehow it's sort of trivial to write down that that's true for integers, because if you can reduce integers mod p, and you can sort of think of integers as being complex numbers, and sort of somehow an identity that holds in the integers sort of holds in the complex numbers and holds mod p. But like these roots of unity, they're not integers. Like they're, I mean, you sort of like complex roots of unity, like you use either 2 pi in, like they're very far from being integers, but and somehow you can sort of write down identities of them that sort of hold just as well of their complex numbers as they hold in finite fields. This is sort of some incredible fact that has a simple explanation, like if you think about it carefully, but when you just look at it, I think it's really, really shocking and incredible and very powerful. Okay, but good. So we have this identity. So this is sort of step one in sort of establishing quadratic reciprocity. And in general, as you use this formula for primitive p root of unity, or sorry, for a square root of plus or minus p in terms of a primitive p root of unity. But it's not just this alone and sort of following the strategy we did above. It's not enough to sort of establish quadratic reciprocity. So it sort of only sort of gets you sort of part of the way there. Because if you just sort of follow through that argument before, what we get is that sort of if you take some, okay, so we have sort of p, and then you sort of take some q that's congruent to 1 mod p, then you're going to get a primitive p root of unity in fq, sort of by sort of the same logic as before. And then you're going to get, using Gauss's formula, a square root of sort of plus or minus p. And if you sort that all out, that'll tell you that sort of p over q is equal to the thing it's supposed to be by quadratic reciprocity. So this sort of some sign times q over p. But here in this q over p is just 1 because q is congruent to 1 mod p. And so really you're just checking p over q is sort of this thing. Okay, and this is something you can check directly using that formula above and sort of just arguing as before. Okay, what we've written looks a little bit different, but I mean, it's the same as sort of what's up there. But in some of this is unlike when sort of p was 2. So when p was 2, like q was either being congruent to 1 mod. Sorry, yeah, when p was 3, q was either congruent to 1 mod 3 or 2 mod 3. And sort of we made this argument to establish exactly what's going on when q was congruent to 1 mod 3. And then sort of somehow the other possibility we could handle because we could reverse Gauss's formula. So we could also handle what happened when q is congruent to 2 mod 3. Here we can only handle what when q is congruent to 1 mod p in general. And like there's no analog of reversing Gauss's formula that lets us handle the rest of the cases. So here we have established quadratic reciprocity when q is congruent to 1 mod p, but we don't know it, like we're quite far still from justifying it when q is not congruent to 1 mod p. So there's sort of many other cases to treat still. And some of the, just to reiterate, the reason this fails, the reason our previous argument fails is because we can't reverse Gauss's formula when p is greater than 3. So we can't go from having a square root to having a primitive p root of unity. So to sort of somehow finish the argument, to sort of finish the justification for quadratic reciprocity, you need a new idea. And so the idea is the following. Well, instead of sort of only working in sort of the fields FQ, where you have a primitive p root of unity, you can take some field FQ that doesn't have a primitive p root of unity, and then sort of put it inside some bigger field where you do have a primitive p root of unity. So that's sort of like going from the real numbers to the complex numbers. So like the real numbers don't contain a primitive third root of unity, because like this formula we wrote down for either 2 pi I over 3, like this has a non-zero imaginary part. So like you can't sort of talk about primitive third roots of unity in the real numbers. But if you want to talk about primitive third roots of unity, you can just go to some place bigger, the complex numbers. Okay. And sort of the same kind of thing here happens here. Like if Q is not congruent to 1 mod P, then sort of you don't have a primitive P through unity in FQ. But you can just replace FQ with a bigger field where you do have a primitive P through unity. Then in that bigger field, you still have Gauss's formula. And then sort of now you just have to sort of understand when that formula in the bigger field actually gives you something inside of FQ. So this is sort of a very powerful, idea, is that you can sort of do all your computations in some bigger place, sort of, and then just sort of check if the result in the end sort of lives in the smaller place. So that's like sort of doing a computation with real numbers by sort of first working with complex numbers, and then sort of in the end sort of just sort of saying, well, okay, but this thing I got like is actually a real number. So actually, this is like one of the most powerful ways to compute integrals. So if you've taken a class or later take a class in complex analysis, you'll find that you can sort of compute many very difficult integrals of real numbers by instead sort of thinking of them as integrals using complex numbers, applying tools that apply to integrals of complex numbers, and then in the end coming back and saying, well, actually what I got is still a real number. Okay, so this is sort of something like that. Now, and it's quite a bit of work still from where we are to go through the full argument that really captures this idea. So what we're going to do instead is we're not going to sort of justify quadratic reciprocity for sort of when Q is bigger than 3. Instead, we're going to go to this other rule that we haven't justified, which was for when 2 is a square mod P. So this rule that says the Legendre symbol of 2, so this is a 2, the Legendre symbol of 2 over P is 1 if P is congruent to 1 or 7 mod 8, and it's -1 if P is congruent to 3 or 5 mod 8. So it turns out in some we're going to use this same idea that I just said here that one uses in establishing the quadratic reciprocity formula. So we need that same idea to establish this law, but that somehow working in this concrete case will be a little bit simpler, and will let us sort of see what the main idea is in so without getting cluttered with having to introduce a whole bunch of new terminology. So we're going to spend the rest of the lecture sort of explaining how to justify this identity, but I just want you to remember that like what goes into sort of explaining the rest of quadratic reciprocity is essentially the same as what goes into explaining this, like once you have Gauss's formula. Okay, so how are we going to do this? Well, the idea is just like before. In order to study when 2 is a square mod P, we're going to express sort of a square root of 2 using sort of roots of unity. And in this case, we're going to use a primitive eighth root of unity. So if in any field, if you have a primitive eighth root of unity, so this is a fact, component fact 1. If in any field you have a primitive eighth root of unity zeta, then if you write down the number zeta plus zeta to the 7, you square it, you get 2. So in other words, zeta plus zeta to the 7, this is a formula for the square root of 2 in whatever field you're in. So yeah, you could justify this just by expanding it out, sort of like we did for a square root of -3. It's a little bit more complicated than that one, but in the end, actually not so much more complicated than that one. And you've done this on the homework, or will do this on the homework if you haven't already, over the complex numbers, and also sort of for some specific examples of finite fields with a primitive eighth root unity. So you'll see some examples. And I guess sort of as an exercise, if you want to understand a little bit deeper, to sort of try and make an argument like we did for primitive third, like we did for the square root of -3, to show that this really holds over any field for any primitive eighth root unity. Okay. But somehow, like the case of quadratic reciprocity where Q is greater than 3, so where p is greater than 3. So like this more general setting of Gauss's theorem, this gives you a way to go from a primitive eighth root of unity to having a square root of 2, but you can't go the other way. So if you have a square root of 2, that doesn't give you a primitive eighth root of unity. Okay. So it's sort of not reversible. So that's why sort of somehow this this argument is still going to capture sort of the essential features of what you have to do in the argument for more general quadratic reciprocity when p is greater than 3. Okay, so that's the first fact. So we have this formula for a square root of 2. Well, in order to use that formula, we have to work in a place where we have a primitive eighth root of unity. Okay, and so my fact 2 says that we can do that. So it says, so if p is an odd prime and you have a field, call it f sub p squared, with p of order p squared, so with p squared elements in it, then in fact, fp squared has a primitive eighth root of unity. So why is this true? Well, the point is, just like sort of fp square, fp cross was sort of isomorphic to z mod p minus 1z, if you sort of argue similarly, you can show that fp squared cross is isomorphic to z mod p squared minus 1z. Okay. And then you can sort of make the same kind of argument and you can say, so, well, so this has an eighth root of unity. So this is sort of some version of the discrete log. I mean, this is, you can think of this as being the discrete log for this bigger field. So in particular, if you sort of follow through the logic from before, this is going to have an eighth root of unity, a primitive eighth root of unity. So again, it's sort of very important that we have a primitive eighth root, not just an eighth root. So a primitive eighth root is one, it's an eighth root of unity that's not a fourth root of unity or a second root of unity. So it has a primitive eighth root of unity. Okay, well, somehow if you're not a fourth root of unity, then you're also not a second root of unity. So that's a little exercise for you. This has a primitive eighth root of unity if 8 divides p squared minus 1. But in fact, this holds for any odd number p. So this is sort of a little exercise to check, but this is just sort of just compute the squares in z mod 8z, and you'll see this. So, okay, so p squared minus 1 is always divisible by 8 for any odd number p, in particular for any odd prime p. And so because of that, like arguing this is a discrete logarithm, just like we did for fp cross, we see that there's a primitive eighth root. Like if you have a field of order p squared, then it has a primitive eighth root of unity inside of it. Okay, so that's sort of a rough explanation of why that fact is true. So okay, so we sort of, if we have a primitive eighth root of unity, we have a formula for the square root of 2. We know that if we sort of have a field of order p squared, then we have a primitive eighth root of unity in there. So now I just have to explain to you why we have a field of order p squared. So that's fact 3, which is if p is not prime, then there exists a field of order p squared. Well, how I can do that? This sort of harks back to these exercises we were looking at earlier in the year when we were doing modular arithmetic with polynomials. And the idea is if So if I take some element D in FP, is not a square. So there are sort of P minus 1/2 choices. This is something we saw last week, that there are P minus 1/2 non-squares in the field of P elements. Well, that means x squared minus D is an irreducible polynomial. In sort of FP brackets X. Okay, and then sort of using modular arithmetic, we see that FPX minus, so FP of X, sort of mod X squared minus D, this is a field. So somehow this was the kind of thing we saw before, that like when you had an irreducible polynomial and you did sort of modular arithmetic mod that polynomial, then sort of you could invert anything else. So you really got a field. And like, because sort of the elements in here are just sort of an element of FP plus sort of multiple, like it's the elements are A plus BX, where A and B and FP. So you have sort of P choices for A and P choices for B. So there are P squared total choices. So there are P squared elements. Okay, so this is a field of order P squared. And again, this is the kind of thing we sort of did some of these constructions earlier on. This is sort of an application of sort of this kind of construction. Is like, now we've seen that we can sort of always find some field that contains FP, but this is some field that contains FP, but where there's a primitive eighth root of unity. Okay, and you can actually sort of say stronger things, so I'm not going to go into that. But for example, like not only is there a field of order P squared, but in fact, sort of there's basically a unique field of order P squared. So you can sort of, there's exactly one in some sense. And well, more generally, this is sort of a very powerful technique. I mean, anytime you sort of want to sort of, you have some field and you have some polynomial, you want to have roots, you can sort of always sort of do something like this to create some bigger field where that polynomial has a root. And this is sort of a very, very powerful method. Okay, but here we just wanted to use it to create some field of order P squared because sort of we were trying to get an eighth root of unity, and a field of P squared sort of suffice for that. Okay, so where are we at? So now if P is an odd prime, we're trying to see when 2 is a square mod P. So let's take that odd prime and let's just sort of create some field FP squared of order P squared. And then once we have that field, so yeah, this fact 3 told us we can do this. Then once we have this field, fact 2 told us that that field contains a primitive eighth root of unity. So let zeta be that primitive eighth root, or a primitive eighth root. And then sort of fact 1 told us that zeta plus zeta to the 7 is a square root of 2 inside this field. And well, there are always at most 2 square roots, because sort of being a square root, it means being sort of a root of a degree 2 polynomial, and any degree 2 polynomial has at most 2 square roots. So it has at most 2 roots. So sort of there are sort of only 2 square roots of at most 2 square roots of 2 in FP squared. So this is one of them, and the other one is just minus of that. So if x is a square root of something, then minus x is also a square root of it. And well, it'll be convenient to write down what that is. So minus zeta plus zeta 7, this other square root is this other square root of 2. This is, I can rewrite this as sort of zeta to the 4th times zeta plus, sorry, my 7s are all over the place. Let me try and fix that. Good. So I can just write this as zeta to the 4th times zeta plus zeta to the 7. That's because zeta to the 4th is equal to -1. And why? Well, zeta is a primitive eighth root of unity. So that means zeta to the fourth is not 1, because otherwise sort of it wouldn't be primitive. But I mean, zeta fourth squared is zeta to the eighth, so that is 1. So zeta to the fourth is something whose square is 1, and it's not 1, so it has to be minus 1. So zeta to the fourth is equal to minus 1. Right, so I can rewrite minus zeta plus zeta 7 as zeta to the fourth times zeta plus zeta to 7. And then I sort of expand that out, and I get zeta to the fifth plus zeta cubed. So the zeta fourth times zeta to 7, that gives me zeta to the 11. But then I know zeta to the 8 is equal to 1, so I can sort of factor out a zeta to the 8 to get just zeta cubed. Okay, good. So these are sort of zeta plus zeta to the 7 and zeta to the fifth plus zeta cubed. These are the 2 square roots of 2 in FP squared. And these are the only 2 square roots. So let me sort of really emphasize that, is that these are the only 2 square roots. Why is that helpful? Because that means like not only do we have a formula for the square root of 2 in FP squared, but like really sort of we know it's like because this formula holds, like we really get all possible square roots of 2. So if we want to now check that there's no square root of 2 in FP, we just have to check that this thing, which like sort of a priori lives in the larger field, FP squared, we have to check that it really doesn't live in FP. Okay, so what we need is then some simple way to check whether an element in FP squared lives in FP. So whether an element of this bigger set is in this smaller set. And it turns out this is equivalent to saying that sort of if I take this element and I raise it to the p power, then I get the same thing. So an element alpha in FP squared is in FP if and only if alpha to the p is equal to alpha. So this is sort of like if I have some complex number, then z is in the real numbers. Z is a real number if and only if it's equal to its complex conjugate. So the complex conjugates are where you just flip the sign of the imaginary part. So this is sort of a powerful way to work with real numbers. Is sort of you can work with complex numbers, and then just sort of remember that the real numbers are the complex numbers that are fixed under complex conjugation. So here, an element in this bigger field FP squared lives inside the smaller field FP if and only if it's sort of fixed when I raise it to the p power. So if and only if alpha to the p is equal to alpha. So here, raising to the p power is somehow behaving like complex conjugation. Okay, so why is that true? How did I set this up? Okay, good. Yes, let me sort of say something about why that's true. Well, so step 1. So alpha to the p equals alpha. It's the same as alpha to the p minus alpha is equal to 0. This is the same as saying alpha is a root of x to the p minus x, which I can sort of factor as x times x to the p minus 1 minus 1. Okay, so now 0 is a root of x. So 0 is a root of just the sort of polynomial x. And by Lagrange's theorem, any element of FP cross okay, so, but sort of FP is just the union of 0 and FP cross. So everything in FP is either 0 or invertible. Good. So this says that sort of every element of FP is a root of this polynomial. But now, and there are P things. X to the P minus X. So, okay, so that sort of says you two things. So first, that says that if you have an element in FP, then it definitely is a root of this polynomial. That sort of definitely does satisfy this equation, alpha to the P is equal to alpha. But moreover, that gives you P roots of this polynomial of the degree P. So FP, and so FP gives P roots. So there can't be any more. So that means sort of by listing out all these roots, like that all these elements in FP are roots of this polynomial, we've exhausted all of the possible roots. And so that means sort of anything else in FP squared can't be a root of this polynomial. So it can't satisfy this equation. Okay, so that tells us we can check whether an element is an FP squared just by checking by whether its P power is equal to itself. Crazy but true. So now, if you sort of trace back everything we've done, then, and we have this, we are working in FP squared, we have a primitive root, a primitive P root of unity, we have this formula for the square root of 2 as zeta plus zeta 7, and we want to check whether or not that's in FP. Okay, and we can do that using this criterion. So we need to sort of check whether when we raise this thing to the P power, whether we get is zeta plus zeta to 7. Okay, so we're going to use one last fact to do this computation. So we're going to use that in this field FP squared, or really any field that contains FP. So if I take A plus B and I raise it to the P power, then that's the same thing as taking A to the P power plus B to the P power. I mean, this sort of looks very naive and not likely to be true. Like if you're used to working over the real numbers, the complex numbers, I mean, certainly adding things and taking like the P power, like adding things and taking the 7th power, that is not the same as sort of just taking the 7 powers and adding them if you have two real numbers. But it turns out this is true. This is a very naive simplification is true in a field that contains FP. So we'll come back and justify this in a second. And this is related to something you guys did on a worksheet a while ago. But just if we admit this fact for now, then we can compute zeta plus zeta to the 7 to the P is just zeta to the P plus zeta to the 7P. Okay, but the point is sort of, this only depends on sort of P mod 8. Just because sort of zeta to the 8 is equal to 1. So like each of these guys only depends on P mod 8. Okay. So, well, if P is congruent to 1 mod 8, this is just zeta to the 1 plus zeta to the 7. So good. So it's in FP. Because, okay, so if P is congruent to 1 mod 8, then when we sort of raise it to the P, this thing to the P power, we really just got the same thing back. So using our condition from before, that means that zeta plus zeta 7 is in FP. So the square root of 2 is in FP. Well, P can't be congruent to 2 mod 8 because it's odd. So, but if P is congruent to 3 mod 8, then we get zeta cubed plus zeta to the 7 times 3 mod 8. So 7 times 3 is 21, which is 5 mod 8. So we get zeta to the 5, which is, by an earlier calculation, minus zeta plus zeta 7. So this was sort of the other square root of 2. Okay, but because this is sort of isn't fixed, like because sort of it's not sort of fixed by raising the p power, that means it's not in fp squared. Sorry, it's not in fp. It is in fp squared, but it's not in fp. Okay. And similarly, if you do this with p is congruent to 5 mod 8, you get zeta cubed plus zeta to the 5th again. And with p is 7 mod 8, you sort of just exchange two terms. So you get sort of zeta 1, zeta to the p is zeta to the 7. So in the p5 mod 8, or sort of not in fp. And when p was 7 mod 8, you are in fp. So square root of 2, which is equal to zeta plus, so plus or minus zeta plus zeta 7. So I only have to check on one of the square roots because they differ by -1. So if one's in fp, the other one's in fp. Plus minus square root of 2, which is plus minus this, is in fp for p congruent to 1 mod 1 or 7 mod 8. And not in fp for p congruent to 3 or 5 mod 8. But that's exactly what we want to show. I mean, this says, square root of 2 is in fp. That's the same as saying 2 is a square in fp, or 2 is a square mod p. So 2 over p is equal to 1 if p is 1 or 7 mod 8, because then we sort of gave this explicit formula for this square root and showed it was in fp. And it's -1 if p is congruent to 3 or 5 mod 8, because then we sort of gave this explicit formula for the square root, and we showed it wasn't in fp. Okay, good. So that sort of finishes the whole justification of this computation of the Legendre symbol for 2 over p. The last thing I wanted to explain was this fact 5 that we used to compute sort of zeta plus zeta 7 to the p. So the fact that we can sort of just pull the p's into each term. So the fact that a plus b to the p is equal to a to the p plus b to the p. So let me sort of pull this down here. Okay. Well, what happens? Let's just do an example first. If I do like, if p is equal to 3, well, a plus b cubed, it's a, so if you sort of just expand this out, you're going to get a plus 3a, sorry, you get a cubed plus 3a squared b plus 3ab squared plus 3b cubed, or plus b cubed. And well, this is equal to a cubed plus b cubed in fp, because sort of 3 is equal to 0 in fp. So sort of these two coefficients in the middle go away because 3 is equal to 0. Okay, so in general, if I look at a plus b to sort of any power, so if I look at a plus b to the nth power, then this is a to the n plus n choose plus n choose 1 times a to the n minus 1 b plus n choose 2 times a to the n minus 2 b squared, and so on all the way up to plus n choose n minus 1 times a times b to the n minus 1, all the way up to plus b to the n. Okay, so these n choose i's, these are not Legendre symbols. This is the binomial coefficients, or they're called binomial coefficients, or earlier we called them sort of the choose function. And we saw this, so we saw these, so it's like n choose I means the number of ways to choose sort of a set of I things from a set of n things. So here, like when you raise a plus b to the nth power, like if you want to sort of get a term that looks like a to the n minus 2 times b squared, you just sort of have like a plus b times a plus b times a plus b sort of n times. And you just have to sort of choose two of these terms to take a b from. And that will sort of give you a b squared, and the rest you'll take an a from, so you'll get a to the n minus 2. And so sort of the number of ways you can get an a to the n minus 2 times b squared is just the number of ways you can choose sort of two terms from n terms. So this is sort of n choose 2. And in general, sort of the coefficient of a to the n minus I times b to the I is going to be n choose I. So you'll have to sort of choose I of these terms to get a b from. Okay. And so we saw on an earlier worksheet that sort of these are given by sort of rows in Pascal's triangle. So these binomial coefficients, you can sort of compute them doing Pascal's triangle, which sort of look like you sort of do ones, and then you add the things above it to get the next row. So you start 1, then 1, 1, then 1. So you always put ones on the edge, and then like, to get this middle term, I added this 1 and this 1, gave me 2. I put a 1 on the edge, and then the next row would be 1. Then I add the 2 and 1 to get 3. I add the next 2 and 1 to get 3. And I get a 1, so on. So for example, this fourth row, 1, 3, 3, 1, that gave me the coefficients when I sort of raised a plus b to the third power. So that's 1, 3, 3, 1. Okay. So that's true in general. And what we saw, the pattern we noticed in that exercise, that earlier worksheet, that we're finally coming back to, is that the p plus first row of Pascal's triangle is 0 mod p. Except for the 2 ones on the end. So except for the ones on either side. Okay, so it's 0 mod p except for the ones on either side, which means exactly that a is sort of a plus b to the p. Well, it's sort of equal to a to the p plus p choose 1 times a to the p minus 1 b, and so on, all the way up to b to the p. And so these coefficients are 0 mod p. So I get sort of a plus b to the p is equal to sort of a to the p plus b to the p. So saying the coefficients are 0 mod p means they're divisible by p. So this is going to be, so those coefficients are sort of 0 whenever p is 0. So e.g. in fp squared or fp. So saying p equals 0 means if you add 1 together p times, you get 0. So that's true in FP, which is z mod pz. But it's also true in FP squared because sort of somehow you can compute adding p together 1 times, adding 1 together p times. So even if you're doing an FP squared, like that computation actually happens entirely in FP. Okay. So maybe now is a good time for you to go back and look at that exercise about Pascal's triangle. I can't remember which week it was, but sometime maybe 4 or 5 weeks ago. Okay, but so once we have that, this is the fact we used to sort of simplify this equation and to use to check sort of whether this to the p power was equal to itself. And then we're really all done verifying this rule for sort of when 2 is a prime mod p. And I just want to emphasize that you really use all of the same ideas for doing quadratic reciprocity when q is larger, when p is larger than 3. It's just sort of a little bit messier to work out. Okay, but we'll stop there, and I will see you all next week. Thanks.